Let's start with one example, kind of still talking about the material we were talking about last time before we move on. So let's say we had the following equation. X squared plus y cubed plus z to the fourth equals 6xyz. And the first question asks us to find del z del x. So really what I want to say here is what this tells you when we're asked to find del z del x, well, we're asking how is z changing as x is changing? Meaning we're imagining both of those are changing. And also we're imagining that y has nothing to do with it. So y is essentially being held constant when we say, okay, how is z changing as a function of how x is changing? The easy way to do this is to first, before I do what I'm about to do here, before I say it was equal to, first, we want to rewrite the equation so it's equal to 0. So rewrite the equation so that we have x squared plus y cubed plus z to the fourth minus 6xyz equal to 0. And now the way we're going to find the partial derivative of z with respect to x is just saying, well, del z del x is going to equal, if we call this whole thing capital F of x, y, z, it's going to be the negative of the partial of f with respect to x divided by the partial of f with respect to z. So I'm always looking at this derivative here and just switching which one's on top, which one's on the bottom, and then putting a negative sign in front of it. We talked about where this came from last time. I'll remind you here just because I do think it's kind of worth remembering. So just as a side note over here, we're imagining, not right, we're essentially starting with f of x comma y comma z equal to 0. And then we're taking the derivative of both sides with respect to x. Again, making the assumption that z is also a function of x. We get to make that assumption because they're telling us to find how z is changing as x is changing. So we're going to assume that z depends on x and that both are changing and that y isn't changing. So we take the derivative of this with respect to x. Well, we're going to get two parts. We're going to get the partial derivative with respect to x. And then we're also going to get the partial with respect to z times the partial of z with respect to x. The derivative of 0 is still 0. This is coming from the fact that we're assuming f depends on both x and z, and z also depends on x. So we're finding all the paths that get us from f to x. Fx is one of them, from there to there, and fz times del z del x is the other path that gets us there. And then if we solve for del z del x, we exactly get fz times del z del x equal to negative fx, which gives us then that del z del x is equal to negative fx divided by fz. You don't have to memorize how to do this. Really, you just have to be able to know that, oh yeah, if you're being asked to find this kind of implicit derivative here, the way to do it is to set this whole thing equal to 0 and then just do the negative of the partial of the bottom thing divided by the partial of the top thing. That's how I remember it. Then we do it. So let's see. So if I look at this whole equation, now I'm just taking partial derivatives like f depends on x, y, and z. So the partial with respect to x is going to be, sorry, the negative sign out in front first, 2x plus 0, and then the derivative of 6xyz is going to be 6yz, but it's negative, so negative 6yz. Divided by the partial with respect to z, derivative of x squared is 0, derivative of y cubed is 0, derivative of z to the fourth is 4z cubed, and then the derivative of negative 6xyz is going to be negative 6xy. And I would probably just leave it like that. You could distribute the minus sign to either the top or the bottom if you wanted to, but leaving it like this is totally fine. That's it. So it's a whole different way of doing implicit differentiation, right? You could also have done this the longer way and had said, oh yeah, I'm differentiating everything with respect to x, and gotten like 2x plus 0 plus 4z cubed times del z del x equal to product rule here, 6 times yz plus 6x times the derivative of yz, which is y times del z del x. And if you do all the solving, which I don't want to do, but if you solve this for del z del x, you would get exactly what we got right there. It's kind of interesting. I know I said I didn't want to do it, but now I'm going to do it because I can't help myself. So we're going to do it anyway, even though I just said I wasn't going to do it. Sorry. So all my del z del x is on the left. You're going to have del z del x times 4z cubed minus 6xy. Oh, looking pretty good. Are we looking pretty good? Did I make a mistake here? I did make a mistake here. So my fz, so actually this is good to see the mistake I made. So going on along here, del z del x times that is equal to 6yz minus 2x. If we divide by that, we should have gotten the same answer. Del z del x is equal to 6yz minus 2x over 4z cubed minus 6xy. Notably, the top is the same. We just would distribute the minus sign, right? That's a negative 2x plus a 6yz. But my bottom is a little bit wrong. I should have 4z, or I've got 4z cubed minus 6x here, 4z cubed minus 6xy there. Let's go back here. When I found fz, the partial of f with respect to z, oh yeah, I forgot to include the y there, right? The derivative of 6xyz with respect to just z should have been 6xy times 1. So there should be a y there. So it does pay to check your answer sometimes. But again, the intent is to do it this way. Yeah. Well, so exactly because of this part over here, right? When I take the derivative of f with respect to x and follow the two paths, I either get the derivative of f with respect to x, which is fx, plus the derivative with respect to z times del z del x, which is that. And then when I subtract this to the other side, that's where the negative is coming from. And then I divide by fz to meaning negative fx over fz. But we can actually even see it here, right? If I factor out a negative from the top, I'm left with negative 6yz plus 2x, all divided by still the same 4z cubed minus 6xy. But look, this thing here is exactly the same as that thing there. So that's how it ends up working out. Cool. Again, not the biggest deal. We don't use this a whole lot, but it is just kind of an interesting result of partial differentiation, partial derivatives. And why does it look like that? Sorry, I forgot to pin my video. There we go. Much better. Okay. Moving along, let's talk about directional derivatives. Well, we'll eventually talk about directional derivatives, but first, a review of some 17B topics. So first, a review. A short review. So a couple things we need to know for this to work. First of all, the dot product of two vectors, say u and v. So there's a couple ways to think about the dot product, and both of them are important. If you have two vectors, say v and u, and we know the angle between them, one way of calculating the dot product, u dot v. I do encourage you when you're writing a dot product to emphasize the fact that there's a dot between them. That's going to equal the magnitude of u times the magnitude of v times cosine of the angle between u and v. But a lot of the time, you won't know the angle between two vectors. And so another way of calculating the dot product, or if we know the components of u and v, say like u is equal to some vector, sure, let's go. Let's say u1, u2, and v is equal to some vector v1, v2, then you can also calculate the dot product by multiplying the corresponding components together. So u1 times v1 and u2 times v2, and then adding up the results. Want to point out when you dot two vectors together, you don't get a vector as the output. You get just a number, also called a scalar. So u dot v is a scalar. For example, if my vectors were u equal to, say, 1, 4, and v equal to 5, 2, then the dot product of u and v would equal 1 times 5 plus 4 times 2, which is 5 plus 8, which is 13. Which doesn't have a really great physical meaning, to be perfectly honest. Like you could kind of think of it in some weird way. It's like it's the amount of one vector in the other direction times the amount of the other vector in the other direction, but it's not really like super useful to try to think about a physical property of it. So that's one thing we need. That's how the dot product works. That's kind of it for now. And then we need something else that I don't think we've ever talked about, but we'll talk about it right now, which is the parametric equation of a line, which is easier than it sounds. Parametric equation of a line. And really, we just need this to help us figure out one other thing. So this is like something we're going to talk about for a brief minute, and then you probably don't need to remember it at all ever. So let's say we have the following. We have a line that goes to the point, say 1, 2, and 4, 7. Here's the way we write the parametric, gosh, words, the parametric equation. So we're going to imagine a particle moving along the line from the point, say 1, 2 at the beginning is equal to 0 to the point 4, 7 at t equals 1 at a constant speed. So basically, from time equals 0 to time equals 1, I'm going to move over 3 and up 5. And then if I went to time equals 2, I would do it again. I'd go over 3 and up 5. And if time was equal to 3, over 3 and up 5 again. Right? I would keep doing that. So how do we find the equation parametrically? Well, the amount that we're increasing x or y by is going to be the coefficient of t. So we're thinking, oh yeah, we need the x as a function of time is equal to the beginning value 1 plus how much we're changing by, which is 4 minus 1, or 3 times t. Similarly, we should be able to find that y as a function of t is equal to an initial value of what? And then we're adding how much times t? Right. And you can see that if you plug in t equals 0, it'll work. T equals 0 gives you 1, 2. T equals 1 gives you 4, 7. If you plugged in t equals 2, you would get 1 plus 6 is 7, 2 plus 10 is 12. You get 7, 12. And then you could let t be any number. Positive, negative, fractional, irrational, whatever. T could be negative pi or negative 1 billion or whatever. Right? So you get all the points going this direction where t is positive and that direction where t is negative. But just like you usually think about a line, it extends forever in both directions. Yes. Sure. So we're just saying, like, let me say one more thing here. So this is how we're describing the equation of the line parametrically, given that t can be any real number. But we're just saying, oh yeah, if you start at time equals 0, well, the x, y coordinate is 1, 2. And then we're definitely going to get that when t is equal to 0. And then if t is equal to 1, right? So t equals 0, we get x, y is equal to 1, 2. If t is equal to 1, we get x, y equal to, let's see, 1 plus 3 is 4, 2 plus 5 is 7. We moved over 3 and up 5. And then you could just keep doing that, right? You could let t equal any number. Like if t equals 2, you're going to get x, y equal to, well, 1 plus 12 is 13. That doesn't seem right. T is 2, not 12. 1 plus 6 is 7, and 2 plus 10 is 12. So we can get any point on the line by just picking the right value of t. And again, this is not really the point of the section. So we're just going to use that to help us do something else. So let's remind ourselves of a previous example that we've talked about, which was the upside down paraboloid. So let's go back and look at the following. So recall the upside down paraboloid. Sure. F of x comma y equal to 9 minus x squared minus y squared, which looks kind of like this. Labeling here. And last time we looked at this, we were specifically interested in the point 1 comma 2 comma 4. If you go up to a height of 4, which is about right there. So this blue circle, that's the level curve when C is equal to 4. And then if we go over 1, over 2, up 1 comma 2 comma 4 is about right there. And I don't want to get too in the way here, so I'm just going to label it over here. So the idea is we would like to be able to find the slope of the surface if we move in any direction from this point. So before we just found the partial derivatives in the x direction. So if you're sitting at that point or standing at that point and moved forward out towards you, we found that the partial derivative with respect to x was negative 2x. And if you plug in the point, fx evaluated at 1 comma 2 comma 4, you get a slope of negative 2 times 1, which is negative 2. So if we move purely in the towards you direction, slope is negative 2. Or if I move purely in the y direction, which is to the right, the partial derivative is negative 2y. And if we plug in the same point, 1 comma 2 comma 4, we're going to get negative 2 times 2, which is negative 4. So if you move to the right, I should say, from your perspective, moving to the right, we're going to go down at a steeper rate, right? It's steeper to move that way than it is to move towards you that way. All right. But now what we'd really like to do is say the following. Move this paper, so I'd really like to do. So suppose we're at that same point. Suppose we are standing at the point 1 comma 2 comma 4. And we want to move in the direction of the vector v equal to, I feel like I want to change this slightly. Sorry, give me one moment. No, we'll do the same. Okay. V equal to 4/5 comma 3/5. Now, when I look at that vector, I don't really think about the values. I think I'm moving essentially 4 in the x direction and 3 in the y direction, or the amount I'm moving in the x direction is 4/3 times as much as the amount I'm moving in the y direction. So a little more in the x than the y. So it's not going to be a perfect like y equals x direction. It's going to be a little tilted that way, so that the x direction is a little more significant than the y direction. Let's say, sorry, let me say one more thing here. Suppose we're standing there at the point, and then what we really want to know is, and find out how steep the slope of the surface is when we move in that direction. That's the question we are answering. I know it's kind of a lot of words. Okay, so even though we're trying to figure out what happens when we move so if we're right here at x equal to 1 and y equal to 2, we're trying to move in the direction of 4/5 in the x direction and 3/5 in the y direction. It's kind of weird to try to draw it here, but we're essentially trying to move. Where's my red pen? Red pen, come back. We're trying to move. Did I lose my red pen? Terrible. Fine, green will do. We're trying to move in this direction. We're trying to move that way, and we're seeing what our slope will be if we move that way. So you might have observed trying to draw this in 3 dimensions is not like it's going very well. So let's just look at the 2-dimensional level curve and then draw the stuff there. So in 2 dimensions, here's how things are going to look. So here's our level curve. Right, so this is when c is equal to 4, so our 4 is equal to 9 minus x squared minus y squared, or in other words, x squared plus y squared is equal to 5. And we're over at the point where x is 1 and y is 2, so about right there. Yeah, where's my red pen? Oh, there it is, hiding. Haha, I found it. Okay, so there's my point 1, comma 2. And from that point, I'm moving in the direction 4/5 to the right, 3/5 up. So that's the direction that we're moving in. So how are we going to find the derivative or the slope in that direction? Well, here's what we're going to do. We're going to start by parameterizing the line that contains that vector. So we're going to parameterize, it's almost like my last name, parameterize the line L that contains the point 1, comma 2 and is in the same direction as V. Well, it's not too terrible. We could imagine that at t equals 0, we're at 1, comma 2. So our line equation is going to be x of 0 is equal to 1 plus something, and x of t, Jesus, James, come on. Sorry, y of t is equal to 2 plus something. And the something we're going to add on is how much we're going to move in the x and or y direction, which is exactly what the vector is telling us. So x of t is going to be 1 plus 4/5 times t, and y of t is going to be 2 plus 3/5 times t. So that at time equals 0, we're at the point 1, comma 2, and at time equal to 1, we've moved exactly 4/5 in the x direction and 3/5 in the y direction. And for the time equal to 2, we're going to move that much over and that much up again and again and again and again and again. So we're definitely describing the entire line that contains this vector. So like there's the line there. Okay, we're building it up. I promise you we're about to get somewhere. So now the question is, how do we find the slope of our function f of x comma y in the direction of the vector v? Well, in other words, the direction of the line L. We're going to use the chain rule. Why are we going to use the chain rule? Good question. So what am I really trying to find? I'm trying to find, again, so again, we're kind of imagining this particle is moving along this line, right? So we're moving along this line, but really that's going to make us move along that line and down the slope. So how are we going to do that? Well, we're going to use the chain rule. We know that our function f depends on what variables? No z, but definitely x and y. F is kind of like our z here. And what do x and y both depend on? T. That's why we needed that parameterization thing, so we could write this dependence relationship. And now we can find this derivative of f with respect to t using the chain rule. It's going to be del f del x times dx dt plus del f del y times dy dt. And although we have actual numbers here, I want to make this simpler. Or I'm going to, simple is not that word. I want to rewrite it. I'm going to rewrite this as the dot product of some vectors. This is the dot product of the vector containing del f del x, comma del f del y, dotted with the vector containing dx dt comma dy dt. So I want to point out a couple things. First and foremost, dx dt is just going to be 4/5, and dy dt is just going to be 3/5. So this dx dt dy dt vector is just your vector v, the direction vector. This vector over here, del f del x del f del y, is called the gradient. And it's given the notation upside down triangle f, the gradient of f. So whenever someone talks about the gradient of a function, it is a vector consisting of all the partial derivatives in order. So if your function is a function of two variables, which is just for the most part in this class, your gradient is just partial with respect to x, comma, partial with respect to y. But if you had a function of x, y, and z, your gradient would be fx, comma, fy, comma, fz. If you had a function of 10 variables, your gradient would be all the partial derivatives in the order that makes sense. Which I know is not really like a useful way to say it, but like the order that you usually list the variables in. Okay, so this is exactly the derivative we're looking for. So this is what's called the directional derivative of f in the direction of v. And it's written the following way. It's written capital D subscript the vector v of the function f is equal to the gradient of f dotted with the vector v. Note, v must be a unit vector. What's a unit vector? No question mark, James. Sorry, it's not a question mark. What is a unit vector? What's special about a unit vector? How long is it? Right. So once you divide the vector by its own magnitude, the new vector will be a unit vector whose length is exactly 1. This vector I gave you already has a length of 1. Right, so if you look at 4/5, comma 3/5, you can see that the square root of 4/5 squared plus 3/5 squared is equal to the square root of 16 over 25 plus 9 over 25. And 16 plus 9 is 25. So you get the square root of 1, which is 1. So if your vector is already a unit vector, there's no need to make it into a unit vector. But if it isn't, then we do need to. So to answer the question that we were starting with, what is the actual value of this directional derivative? Well, our directional derivative, in this case, our gradient is the, it's negative 2x, comma, negative 2y. And we're going to have to evaluate that at the point of interest, which is 1, comma 2, comma 4, dotted with the vector 4/5, comma 3/5. So plugging in those points, we get, let's see, negative 2, comma negative 4, dotted with 4/5, comma 3/5. If we multiply this out, we get negative 2 times 4/5 plus negative 4 times 3/5, which adds up to negative 20 over 5, which is negative 4. So, way back here, from this point on this surface, if we move in that direction, we're going to be going down with the slope of negative 4, meaning if we move 1 in that direction, we're going to go down 4 units. Or at least we would if that was like the slope the whole time. So, question? Oh, thank you. Yes, good call. Let's just say it again. Yeah. So we could ask more questions like, for example, what is the slope of f of x comma y equal to the same function still, 9 minus x minus y squared at the point 1, comma 2, comma 4 in the direction of the vector 3 comma -1. So again, we have to find our gradient. Same gradient, right? Our gradient is still, well, at least before we plug in any values, our gradient is still -2x comma -2y. And then at the point of interest, which is this point right here, our x value is 1, our y value is 2. So our gradient evaluated at 1 comma 2 comma 4 is just going to be the vector -2 comma -4. Same as it was in the previous problem, right? Because the gradient at any particular point doesn't change. What's going to change is the slope of the surface if we point in a different direction. So now instead of pointing in the 3/5 comma 4/5 direction, we're pointing in the x equals 3 and y equals -1 direction. So we're definitely going a different way. So we're going to dot this with our u is what we usually call the, I should have used u before, I didn't. But the unit vector here is going to be r vector v divided by its own magnitude, which is going to end up being the vector 3 comma -1 divided by the square root of 3 squared plus -1 squared. Or as I would probably prefer to write it, 1 over root 10 times 3 comma -1. I don't think it is worth your while to distribute that 1 over root 10 to each of the terms. You don't need to write root 10 more than once. You can, but it's really not going to play a role in your calculations until like the very end. Or at least if you're doing the least amount of work, it isn't. So then, to find our directional derivative, our du of f, which I feel like, oh yeah, I'm sure, it's going to be equal to this dot that. So -2 comma -4 dotted with 3 comma -1 divided by root 10. So do the dot product first. It's going to be -2 times 3 plus -4 times -1, all divided by the square root of 10, which is -2 over root 10. So different direction means we got a different slope. Let me give you all one to try on your own. So here's our new function. F of x comma y is equal to 5xy squared minus 4x squared y. And I want to find the directional derivative of this function at the point what do we got here? 1 comma 2 in the direction. I'm going to give it to you as a unit vector in the direction u equal to 5/13 comma 12/13. So your job, find the gradient, plug in the point, not the vector, plug in the point, and then dot that with the vector. All right, so let's see here. Our gradient, just leaving the x's and y's, is going to be the partial with respect to x is going to be 5y squared minus 8xy. And the partial with respect to y is going to be 10xy minus 4x squared. Now, if we plug in our point, our gradient at the point was 1 comma 2. Again, it's going to be, and be careful here. It's going to be easy to plug in the wrong thing for x and y because it's often easy. Like you think plug in the first thing first. But 5 times y squared, that's going to be 5 times 2 squared minus 8 times 1 times 2, comma 10 times 1 times 2 minus 4 times 1 squared. That's going to be 20 minus 16, so 4, and then 20 minus 4, which is 16. Hopefully we all got the same thing. Hopefully I got the right thing. Check my notes. Interesting. Someone writing these notes before clearly made a mistake. Well, that looks right, right? Good, okay. So then our directional derivative is just going to equal 4 comma 16 dotted with my 5/13 comma 12/13 direction vector, which is going to be, so I'm going to ignore the 16. It's going to be 4 times, sorry, the 13. 4 times 5 is 20 over 13, and 16 times 12 is something. I don't know, what's 16 times 12? 160 plus 32, 192. So we end up getting 212 divided by 13. Pretty steep, right? If you're on that surface, I mean, this surface is probably bizarre looking, or at least kind of probably does a lot of this, but like this is like that's bigger than 10 by a lot. If your slope is 10, right? You're going over 1 and up 10 units. That's a steep surface to be going up. Definitely don't want to be skiing on that. People do ask skiing questions, by the way, with these. You're skiing down a slope and you want to find some sort of easy way to get down. What did you do? Let's see, what time is it? Let's do one more example. So here, let's look at this next example and talk about kind of how to make it more approachable. So we want to find the directional derivative of f of xy equal to 1 plus 2x times the square root of y at the point 3 comma 4 in the direction of, I'm going to give you something really terrible. Sure. V equal to 6 over 23 comma negative 8 over 23. Which is definitely not a unit vector on its own. If it was, I would have called it U. Also, it's not because its magnitude isn't 1. So let's just proceed as usual. So first we're going to find the gradient of f. Some partial derivative. So the partial of this with respect to x is going to be 2 times the square root of y. And the partial of this with respect to y is going to be 2 times x times the derivative of y to the 1/2 is 1/2 times y to the negative 1/2. Interesting. And then if we plug in our point, 3 comma 4, we're going to get, you can use either notation. You can use this vertical line notation, or you can use this parentheses notation. Either way is fine. It's going to be 2 times the square root of 4. I'm going to cancel the 2 and the 1/2 there, and I'm going to get, that's going to be x times y to the 1/2, sorry, negative 1/2, or x over the square root of y. So I'm going to get 3 over the square root of 4. Which ends up being 2 times 2, comma 3 over 2. So there's my gradient vector. And then I want to go in the direction of this vector of 6 over 23, comma negative 8 over 23. I really don't want to divide that vector by its own magnitude. Its magnitude is going to be gross, right? The magnitude of v is the square root of 6 squared over 23 squared plus -8 squared over 23 squared. There's a better way. So here's the thing. That vector v points in some direction, right? Over 6 down here. V does something like this. It points that way. You know what else points in the same direction? Any multiple of v. So if I took, say, the vector, I don't know, 23 times v, which is equal to the vector 6 comma -8, either one of those, if you divide it by its own magnitude, will be a vector that points in the same direction with a length of 1. So if you're ever trying to normalize, which is when you make a vector into a length 1, a vector, and it looks kind of crappy, you can make it nicer before you normalize it. You're allowed to multiply it by any non-zero number you want before you normalize it. So if you've got terrible fractions, multiply by the denominator, get rid of the denominator. This vector now, I'm going to find the unit vector in the same direction. So my vector u is going to be 6 comma -8 divided by the square root of 6 squared plus -8 squared, which happens to be the square root of 36 plus 64, which is the square root of 100, which is 10. This actually happens to be the vector 6 over 10 comma -8 over 10. Or if you reduce those fractions, 3 over 5 comma -4 over 5. You would get the same result if you divided this vector by this terrible magnitude. It would just take a lot more work to get to the same nice place. So now our derivative is going to equal the gradient 4 comma 3 halves dotted with our unit vector, which is 3/5 comma -4/5. And then we multiply it out. I should say we dot product it out. 4 times 3/5 is 12/5 plus 3 halves times -4/5 is -12/10, which reduces to 12/5 minus 6/5, which is +6/5. A positive slope, meaning we're going up the hill versus down the hill, or up the surface versus down the surface. What time do I have? So looking towards the next thing we talk about with this, I'll say one more thing here. So for this same example still, what direction should we point in to have a maximum value for the directional derivative? Good question. Well, to answer this question, let's actually go back and look at how we define the directional derivative in the first place. I'll remind you, our directional derivative is equal to the gradient of f dotted with the vector u, where u is a unit vector. And one way you could find this, if you knew the angle between the two vectors, would be that it's just the magnitude of the gradient times the magnitude of the vector u times cosine of the angle between them. But what's the magnitude of the unit vector u? It's 1. And cosine of theta, what's the biggest cosine theta can ever be? You can't, so 1's the value we get by putting in, not pi, but I think 0 actually, right? Yeah, cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is -1, but the maximum output value you can get for cosine and sine is +1, and the minimum is -1. So no matter what, this whole quantity is going to be less than or equal to the magnitude of the gradient times 1 times 1. Or in other words, the magnitude of the gradient is the maximum value we can get. And you're going to get it when the angle between the vector and the direction vector is what angle? What angle gives us a cosine value of 1? 0. If the angle between two vectors is 0, that means they point in the same direction. So in other words, we're going to maximize the directional derivative, or if you like to say it this way, the slope, the steepness of the slope is as steep as possible if you move in the direction of the gradient. Right? Because if you're thinking about being on a hillside, right, you could be on the point where you're moving, going directly up the hill, or if you're going to the side, like doing like a switchback kind of thing and going up very gradually, or even turning around and going down the hill where your derivative is negative. So the direction where the derivative is the biggest it can be is the direction of the gradient vector. So this is maximized when our direction vector u is equal to the direction of the gradient, which is the magnitude of the gradient, is the gradient divided by the magnitude of the gradient. And that's something that's important to remember, that we can maximize this directional derivative if we point in the direction of the gradient vector at that particular point. So in this previous example, if we look back here, okay, well, our gradient at the point, what was it? 3, 4, our gradient was equal to the vector 4, 3/2. So there's two things I want to say, and then we'll wrap it, we'll be done. So thing one, the derivative, the directional derivative will be maximized if u is equal to that vector, 4, 3/2, divided by the magnitude of that, which is the square root. So here's where I did something that's, I could have done better. So check this out. I'm going to do it this way. I made 4 squared plus 3/2 squared. You know what I could have done instead? I could have gotten rid of the fractions first. I could have instead said, oh, let's just multiply this vector by 2. So 2 times the gradient at the point 3, 4 is equal to 8, 3. And then my vector u, I could more easily write as the vector 8, 3 divided by the square root of 64 plus 9. Those are the same. This one just looks nicer. So here our vector is 8, 3 divided by the square root of 73. Okay, and then the other thing I want to point out is, what is the maximum value? What is the steepest slope we can get? Well, again, if you look at the directional derivative, the most this can ever be is the magnitude of the gradient. So our maximum value of the directional derivative is going to be the magnitude of the gradient of f, which unfortunately we do have to do, right? We can't just multiply the vector by whatever we want to. It is going to be the magnitude of the vector 4, 3/2. So it's going to equal the square root of 4 squared plus 2 squared, which is equal to what? I don't know. It's the square root of 73 over 4. Okay, so this comes up relatively often in this section, but if you're ever trying to maximize something, you want to point in the direction of the gradient, and the maximum value is the magnitude of the gradient. We'll say more about that on Wednesday.